Okay, so our next speaker, who has actually been instrumental anyways in this whole symposium, is Aditya Guha from ISI Kolkata. He will talk about random walks on networks. Over to you.
Yes, so today I'll be speaking of random walks on networks, which can be rephrased as reversible Markov chains revisited, because these are essentially reversible Markov chains. So the class of reversible Markov chains and the class of random walk on networks are essentially the same, but viewing a reversible Markov chain as a random walk on a network is beneficial for quite a few reasons, and we shall see one of them today. Okay, so yeah, so before I begin, I'll just briefly comment on the setting that I'm assuming in this for this talk. So by a Markov chain, here we will mean a discrete time Markov chain on a finite or countably infinite state space, and so that is a sequence of random variables xt t belonging to the non-negative integers, which takes values in some countable or finite state space x, and such that for any t non-negative t, and for any a0 to at, which are subsets of the state space x, for satisfying this condition that the probability of xt belongs to at, xt minus 1 belongs to at minus 1, all the way up to x naught belongs to a naught, is non-zero. And for any y belongs to x, we have this conditional probability of xt plus 1 equals to y, given xt belongs to at and x naught belongs to a naught, is equals to a probability of the conditional probability that xt plus 1 equals to y, given xt belongs to at. So this essentially means that in the presence of knowledge about xt, for determining anything about xt plus 1, the past is irrelevant, is redundant. Okay. So this is the basic setting that that will be assumed throughout the lecture. Okay, so a Markov chain, or more generally a transition kernel or stochastic matrix P on a state space X is said to be reversible if there is a non-zero finite measure pi on X satisfying the detailed balance equations pi X times P xy is pi y times P yx for every X and Y in the state space. So this means that if we start according to a distribution pi, then we take the first step, and we want to reach y. So say we start at x and we reach y. That event has the same that is exactly, I mean, that probability is same as the one that we start at y and we that starting at y we reach x. So it essentially means that if you look at the pair x0 x1 and the pair x1 x0, these two random vectors or these two pairs have exactly the same distribution. And it can be actually amplified to show that the distribution of any, if we have a reversible Markov chain xt, and if we have any n, which is a non-negative integer, and if we start the Markov chain x at x0, which follow with where x0 follows pi, then that's a reversible measure. Then the tuple x0 to xn has the same distribution as the tuple x0 to xn to x0. So in other words, colloquially, it can be stated as if you are watching as a Markov chain as a movie evolving over time, and if you play the movie backwards, then for a reversible, the reversible condition essentially says that the two movies have exactly the same distribution. Okay, so in case x is finite, then of course the summation of pi I values will be finite, and then in that case we can normalize pi to a probability measure on x. That essentially makes more sense, because that allows us to make statements like we have the initial state is chosen according to a probability distribution pi, and so on. All right, so here I'll just mention a few examples and an interesting non-example. So simple symmetric random walks on graphs are reversible. So by simple symmetric random walk on a graph, I mean that we have a graph, and at each vertex, the particle travels along one of the edges that leaves that vertex, and the edge is chosen uniformly at random. So there's no particular preference for a single edge over the others. Okay. Then there is another example is so this is reversible, and in fact in this case it is easy to find the reversing measure. Pi is called a reversing measure, by the way. It's easy to find the reversing measure, and in this case the reversing measure would be just the degree of the vertex divided by sum of all the degrees, because that's the proportion in which the things get allocated, the weights get allocated. Okay. So now there's another example is the random walk on line graph. So here we have n vertices, n vertices all on the same line, And from any of the intermediate vertices, we accept these two endpoints marked with orange, with any of these blue n-2 points, we move to the left neighbor with probability 2/3 and to the right neighbor with probability 1/3. And when we reach those orange vertices, that is the endpoints, we just move to the neighbor with probability 1 in the next step. So these are sort of the reflected barriers, and the remaining is the 2/3, 1/3 biased random walk. So this random walk is reversible, and in fact, it's not difficult to find the reversing measure for this random walk. But the main point why I'm putting it here is because a slight detour of it makes the random walk completely different. So it makes it not reversible, irreversible. So you consider, suppose now you take this line graph and you stitch together these two ends. So you get an n cycle, and in that n cycle, this transition rule essentially becomes same as saying that you move to the anti-clockwise neighbor with probability 2/3 and to the clockwise neighbor with probability 1/3. Okay. So this is not reversible, and actually there is a easier way to show that this is not reversible than to show that the line graph, the random walk, is reversible. So the way we show it as, suppose that the random walk on this n cycle was reversible, then there existed a reversing measure or a pi for which pi y times p y x is pi x times p x y. Now, in this when you have a circle, since the random walk is just since the probability of moving in the anti-clockwise direction is just twice the probability of moving in the clockwise direction, so you see that to balance this equation, pi y times p y x times is equals to pi x times p x y, to balance this equation, one essentially needs to multiply the pi I values by 2 each time it moves to the clockwise direction. So if b is a clockwise neighbor of a, then one has pi b is twice pi a is twice pi b. And in this way, in this case, it keeps on multiplying by twice, and but eventually, since we have only finally many vertices all on a circle, so we will reach back this point where we started from, and then we get a contradiction. Then we get something absurd, that we cannot have pi a equals to 2 to the power n times pi a if pi a is non-zero and finite. So this shows that this random walk on the n cycle is not reversible. Now, this actually had a very nice way of visualizing this result, because we could speak about things like it moves and the mass keeps increasing each time we move to the clockwise neighbor. But in this case also, one may think that the same such thing happens, that when we move to the left, the mass keeps increasing, doubling, and that's actually right, because except at the endpoints, the mass is actually with twice probability we move to the left and to the right. Then what's the difference between this example and the n cycle example, which causes this difference of the behavior, which makes them totally different? So the main crux here is that if we start according to the distribution pi, then only we can say that the forward chain, that's x naught to xn, and the backward chain xn to x naught have the same distribution. Otherwise, we can't say anything like that. So, and here we see that in this line graph example, if we compute the reversing measure, that will also be the stationary measure. And if we start according to that, then we will be more or less concentrated towards one end of the line graph than over the entire uniformly. We won't be uniformly choosing a vertex, any of them vertex if we start according to the reversing measure. The reversing measure puts more weight towards one end of the line graph than towards the remaining parts. So it's like we keep on bumping to that end of the line graph, and that's not that's not anything to worry us, because that's okay, right? All right. So now then, since we have seen quite a few examples of reversible Markov chains, without further ado, I'll move on to the main crux of this talk, which is random walk networks. Before that, I'll discuss about harmonic functions, which are very short discussion of harmonic functions. So a function hx to r, the real world function, is said to be harmonic at a vertex x if we have hx equals to the summation over all y in the state space hy times pxy. So this quantity on the right hand side, summation, this thing, and this can be viewed as a one step into the future. So like we start at x, we move to y, and then we multiply it by hy. So we are moving one step into the future, and here we have hx. And actually, this concept also expands to the more more general concept of harmonic functions, as which as many applications in different fields, including complex analysis, because they are the real part of our holomorphic functions and many other places. So this thing expands there, and I think that there is a nice discussion on this in, I think, in Folland's book, Gerald Folland's book. So like they try to motivate how harmonicity is important and how it's relevant to both the scenarios. All right, so now we have this harmonic extension principle, which will be very useful for us throughout this lecture. So suppose we have an irreducible Markov chain. So an irreducible Markov chain is one where for any two vertices, we can find a time point n such that one can move for the positive probability from one of those vertices to the other in that time, in that n, in n many steps. So this harmonic extension principle, suppose we have an irreducible Markov chain xt on a state space x, and suppose B is a subset of X, and we have a real valued function HB defined on B. Then the function which maps X to the expected value of X, expected value start that the particle starts at the conditional expectation that of HB X tau B, given that the particle starts at X. This is the unique extension of HB to the state space X, which is harmonic on the remaining part of the state space, that is on X set minus B. And here I would like to say that X tau B essentially means that it denotes the first time the particle reaches a state which belongs to B. So X tau B is the first state of B that is visited by the particle, by the random walk. Okay. All right. So this is the harmonic extension principle. Unfortunately, I won't discuss the proof of it because there are several parts, several results to follow, and I'll skip the gloss of the proof of it. Now let's discuss about random walk on networks. So we will borrow some terminologies from physics or from electrical circuits, because they help us give a better insight of what's happening, and the notions actually fall in place very nicely. So this was a work I think was developed by Doyle and Snell, and ever since then it has expanded and it has found applications in many things. Also, actually, I would like to share that I recently heard this story that Feller once proposed a problem to Doob, and Doob at that time didn't know about this random walker networks. So the problem was the problem became quite non-trivial and very difficult if one doesn't use any ingredients of random walker networks. So essentially, Doob couldn't solve that problem until he learned about the theory of random walker networks, and then he used that to solve that problem. So we can understand that how rich a theory this is, because someone as prolific as Doob was stuck on a problem for so long, and he had to entirely study a new theory to follow up on that problem. All right, so now a network is an edge-weighted graph. So that means that we have a graph and we put some weights on the edges. Unlike the case of simple random walk on a graph where we said that there were no particular preferences for visiting via any particular edge over the other. Here we have some particular preferences over visiting via a particular edge over the other. So a way to think of it in terms of electrical circuit theory, or in terms of electrical circuit, is that this weights sort of represent the conductance of the resistance. So like the more the weights, the more the chances of the particle traveling via that or via that edge. So that's the statement in the second line. So a simple random walk on this network visits at each step a neighbor which present location, with the probabilities of transitions to various neighbors are proportional to the weights on the edge joining these vertices to its present location. Okay, so this is a simple random walk on a network, and also I'll define two more terms. So as I said at that time, so it's better if we think of these weights as conductances. The higher the conductance, the more the chances that particle flows, the electron flows along that. So in this case, the higher the weight, the more the chances that the random walk visits along that edge. And reciprocal of conductance will be called resistance. This again is attributed to the terminology that physicists use. And again, yeah, here one draws the analogy that higher the conductance of the edge, the more is the probability of transition along that edge. Also, for any node A of the network, so the points of the vertices of the graph in case when we are speaking on terminology of networks and conductances, we will call these vertices as nodes. So any node A of a network, we shall write CA to denote the sum of all the conductances on the edges that are incident to the node A. So we collect all those edges that have one endpoint as A. We sum their conductances up, and we call that quantity as CA. Okay. So now formally the transition probabilities of the Markov of the random walk on this network is given as follows. So we consider the Markov chain on the vertices of the network G. So G is the network that we're speaking about so long, with the transit, and it has a transition matrix P, which has the Pxy is Cxy by Cx, where Cxy is the conductance on the edge joining X and Y, and Cx is as we just defined. And here we should note that even if there is someone, so it may arise that there may be some edges which are absent. So in that case, so a priori this doesn't make sense in that case, because we are not defining xy, cxy if x and y are not adjacent. But in what I am doing, I'll be stating that if some edge is absent, I'll just define the conductance of that edge to be 0. So that means with 0 probability, the particle moves along that edge, and so everything remains what we have in the way we want it to, and so it's fine. Okay, so this makes this definition unambiguous, and we have a proper definition. So this random actually, and this Markov chain is actually reversible with respect to the reversible measure pi x. Pi x is given by cx divided by summation over y cy. So this is the total conductance at all the nodes, and this is the conductance at the node x. And it's easy to see that pi x is add up to 1. And again, if you just plug in pi x times pxy, it will be just cx, and cx will get cancelled, cxy times summation over y cy, and that's essentially yx times summation over x cx, because this is just the same thing, cxy cyx, and that becomes same as pi y times pyx. So this is indeed the reversing measure for the random walk on a network. And more interestingly, one has that any reversible Markov chain can be modeled as a random walk on a network. So this actually justifies our starting title, that random walk on networks or reversible Markov chains revisited. So reversible Markov chains, the class of reversible Markov chains is no different than the class of all random walks of all random walk on networks. And actually, this construction is not difficult. It's just we have to just pick in the pxy's properly. So we are given the pi x. So in this case, we got pi x from pxy's. In that case, we have to just backtrack, and we are given pi x. We have to move and find what pxy should be. Okay. All right. So now the more terminologies. So we shall define for a network GCE. As the CE means that I am defining the sequence of the collection of conductance values of each edge of the network. So for given a network GCE, we distinguish two vertices of the network as the source and the sink. So we shall write A to denote the source and Z to denote the sink. And voltage is a function defined on the state space X, or the set of vertices of G. So X is the set of all vertices of G, which is harmonic on all the vertices except at the source and the sink. And thanks to the harmonic extension principle, we know that if we are given the values of H at of a voltage at the source and the sink, then there exists a unique voltage for the entire graph for the entire network, or a unique harmonic extension of it. So then which is harmonic on X set minus this source and sink. And thus this is the thing that so thanks to harmonic extension principle, the voltage is uniquely determined by its values at the sink and the source. All right. So again, so now we shall also slightly detour to a new notation. So an oriented, we shall call an oriented edge. So given, so earlier we defined graphs. When we define graphs, we usually say don't distinguish between an edge joining X and Y and an edge joining Y and X. They are viewed the same. But there is again, yeah, there are notions of graphs, the directed graphs, where people make these distinctions. And we shall also do that distinction in this case. So an oriented edge is an ordered pair of vertices of a network. So here we are trying to give a sort of direction to each of the edges, and the way to understand it better is like if you contrast it with road networks. So like some roads have one ways, so we cannot travel in both directions in those roads. So this is how the oriented edges look like. So, and a flow is a function theta on oriented edges, which is anti-symmetry. That is the function that is theta times theta of xy, the theta of the edge that takes x to y is just my negative of theta of the edge that starts from y and ends at x. And here unlike the notion of directed graphs, so like in directed graphs we have sometimes we say that there is an edge from x to y, but there may not be an edge from y to x. Here we assume that whenever there is an edge from x to y, there's another edge from y to x, and the flow on that edge from x to y is just negative of the flow from on the edge from y to x. So this is a this is the setup, and we define divergence of a flow at a node x, so at a vertex x, and denote it by div theta x, subscript theta x, and that is a summation of all the flow values of the edges that start at x and end in some other vertex of the graph. So here I've written y till x to denote that y and x are neighbors in this graph. And as I mentioned, that since we have a graph, if we have a edge from x to y, we also have a edge from y to x. So it doesn't matter that it doesn't. So we don't need to say that y there is an edge from x to y. We can just say that there is the y and x are edges, because that's equally good in this case, thanks to our way of putting it. Yeah. So now we have this divergence conservation principle, which says that for a flow in a network, the divergences of all nodes add up to 0. Before I'm going to prove, we see that this essentially means that we cannot create new divergences by sending a flow, or we cannot destroy divergences by sending a flow. And the proof is very simple. By using a double counting argument, we see that if theta is a flow, then one has when we sum over the divergence of all x, we can just break this sum into two components, which is by definition it is a sum of x, sum over x, summation y is adjacent to x, theta xy. So we are just unfolding the definition here, and this can be broken into this can be split into two ways. So we instead of summing it in this way, we sum at this as we just consider summing over all x and y such that x and y are neighbors. And we have seen that in this case, due to symmetry, we have if x and y are neighbors, then y and x are neighbors. So, and then we add up theta xy plus theta yx. Now, due to and thanks to anti-symmetry of a flow, we have theta xy plus theta yx is 0 for each such x and y. So this summation is, so the entire sum is 0, and we get what we want. All right. So now I'll define a particular. So this was a general flow. Now there is a particular class of flows which we shall be more interested to work with. So this shall be called a flow from the source to the sink. And so this is a flow theta, which satisfies Kirchhoff's node law. That is, the divergence of theta at any node other than the source and the sink is 0, and divergence of the flow at theta divergence of flow theta at the source is non-negative. So this can be interpreted intuitively as saying that the source of a network is where all the flow originates, and so this is what part 2 means, that we have it is a source of all the things of the flow, and part 1 says, and Kirchhoff's node law says that flow cannot accumulate or be created at any of the nodes, intermediate nodes. So that's essentially the thing, and we define another notion called strength of a flow. So that means that it is the divergence of the flow evaluated at the source. So, and this definition can be contrasted with what we have written here, that the flow originates at the source. So the higher the strength of a flow, the higher the value of the divergence at a flow at the source, the higher is the strength of the flow. So the strength is a word that fits in this context. So strength of flow. And the unit flow is a flow that has unit strength. The strength is 1. And thanks to divergence conservation principle, it follows that the strength of a node is the divergence of the flow at A, which is negative of divergence of the flow at the sink. Okay, so now we have, since we have defined flows for so long, so we see that it's defined for oriented edges. Now there were some two notions, that of conductance and resistance, which were defined for unoriented edges. So we would like to somehow fit these definitions for oriented edges so that working with them becomes easier, writing becomes easier. We do it in the most naive way. So we just define the C of the oriented edge xy to be C of the unoriented edge xy. and similarly resistance. And but unlike here, one should note that unlike flows, which are these conductors and resistance, this for oriented lasers, these things are not antisymmetric, but these are actually rather symmetric. One has Cxy is C of another xy, which is C of another yx, which is C of yx. And similarly for the resistance. All right. So now, since we have defined voltage, resistances, the next thing that comes to our mind is current, and we shall define current. So, given a flow voltage W, the voltage function W, as we call the current flow and the network. So the network already has this conductances. So we are not asking for conductance at each step. The conductances are already there, and the voltage something that is added to it. So that will create a current flow rate. So the current flow that is associated with W is a flow I, which is given by I flowing on the edge xy is Cxy times the potential difference. So this is sometimes called potential difference in physics. So times Wx minus Wy. And equivalently, if we just write Cxy as 1 by Rxy, then we get it's Wx minus Wy divided by Rxy. And that's also the how we have defined currents when we were learning them in high school in physics courses. Okay, so but we have seen that it's a flow. I is a flow, but we should we should do justice to that terminology. So it's easy to verify that I is actually antisymmetric because Rxy is Ryx, Wx minus Wy is negative of Wy minus Wx, so it's antisymmetric. And thanks to harmonicity of the voltage at all nodes, except at the source and the sink, one has that x at every node x other than the source and the sink. If we sum over Ixy such as over y, where y is adjacent to x, so this sum split it can be unfolded as Cxy times Wx minus Wy, and this sum then becomes summation over z adjacent to x, Cxz times Wx minus the sum of Wy times Pxy. So this here we are unfolding the Cxy. We are introducing definition of Pxy that we have just said, and thanks to harmonicity, this component is 0. Hence, each of the summands is 0. This entire sum is 0. And this verifies the Kirchhoff's law, and this essentially allows us to conclude that the current flowing from source to sink is indeed a flow from the source to sink of an inner network. And another, so from our the conventions that we have developed so far, several other laws of electrical circuits fall in place with this definition of current. For example, the famous Ohm's law, which says that the resistance times the current is the potential difference, is just a consequence of our definition, how we defined it. So it's fine. Now we come to an important result, which again without proof because because of time constraints, there's many time constraints. So I'm not mainly because I wanted to keep the slide more concise and together, bound together. So a node is called node law, cycle law. So it says that suppose we have finite network. So the number of vertices in this network is finite, and if we have theta is a flow from the source to the sink, it satisfies the cycle law. The cycle law says that when we are summing up the flow times the resistance along each edge, this directed edge of a cycle. That is, it starts at the same vertex. We move by an edge, again by an edge, and so on and so forth. We reach the same vertex where we started from, and along each edge we have the theta ei, and we have the rei. So we have multiplied rei times theta ei, and we add up this product, and this should be 0. If theta is such a flow, then we say that theta satisfies cycle law. So for a finite network, if theta satisfies the flow from A to Z, it satisfies the cycle law. And if theta is equals to the current flowing through that, if the strength of theta is equal to the strength of current flowing through it, then theta equals to I. And in fact, it can be said more that if the strength of theta is some positive constant C times its current, the strength of I, then theta equals to C times I. The flow value as theta over any edge is C times the current value over that edge. In particular, we get this. So this is a quite interesting result. And actually, the way the main utility of this result will be to show that certain flows are currents, and we will have some results about currents. Then we can use this result to show that some particular flow is a current, and then we can use those results that we have known about currents to for this flow, and then we get to derive conclusions. That would be the big picture of how these things are used. All right, so now we have the definition of effective resistance.
Just to let you know, it's about 10:45 already, 10:47 right now. So you're already
Uh,
almost
I,
full time.
oh, okay. I think I'll take 5 minutes maybe. Yeah.
Sure.
Hmm. So I'll just quickly wrap up. So the effective resistance is a quantity Ra to Z. So it's the potential difference between Wa minus Wz divided by the strength of the current. And the name is justified because if we remove all the edges of a network by a single edge that joins to the source and sink, then this is essentially the resistance that we need for the flow to be, so the current to remain the same. All right. So now there are some notions of heating time. The heating time is the tau A is the first time the particle visits the node A. First return time to A is the first time the particle returns to A, given that starts at A. And heating time of two subsets is the first time the particle hits some vertex which belongs to the A. So the effective resistance, sorry sir, but I think the next talk is scheduled at 11, right? So can I continue for a
Uh,
couple of
11, sure. I mean, you can continue for like 10 minutes maybe.
yeah, 10 minutes. I should. 10 minutes would be a good time to complete.
Okay, sure.
Thank you. Yeah. So now effective resistance. So we shall. So these are the hitting types. So we are now entering the realm of probability. So now we have discussed about effective resistance and such things. So now shall we like to connect it with those of escape probabilities. So the suppose we have a network whose vertex set is x, and we distinguish two vertices at the source and sink, which are a and z, and a source is not equal to a sink. Then starting at the source, the probability that we would reach the sink before making a revisit at the source is essentially equals to 1 by conductors accumulated at a ca times the effective resistance between a and z. And the proof will hinge very heavily on the harmonic extension principle. So suppose we set B as the set source comma sink, and we say HB is the indicator of the sink. So it's one if B is chosen, if B is chosen from A, from this set, and B is A and is zero, is one if B is equal to Z and zero otherwise. Then by the harmonic extension principle, we know that there exists a unique harmonic extension, which is given by x maps to expectation starting at x, hb of x tau b. And in this case, this expectation, since this is an indicator, so this turns out to be probability that starting at x, tau z is less than tau a. And here, note that here is not tau a plus, but tau a, because we are starting at x, which is not a. Okay, and is a unique extension of hb on x. It's a harmonic on x set minus az, which values 0 at a and 1 at z. But also notice that this function x maps to wa minus wx divided by wa minus wz is harmonic, because w is a voltage is a harmonic function. We scale the voltage by something, so that also remains harmonic, because the scalings just enter each command and they come out. And we subtract it from something, so the remaining quantity is also harmonic. So a linear combination of harmonic functions is harmonic. Thus, as a result of this function is also harmonic. As a result of that, so we see that these two extensions must be equal by the uniqueness of the harmonic extension. So now we write P A tau z less than tau a plus A has summation over x not equals to a and z. PAX, that is the probability of moving from a to x in one step, times px, the starting at x, the tau z is less than tau a. And expressing the transition probability PAX in terms of the conductances on the edges, leaving A, and rearranging the obtained equations, we get the proof, we complete the proof of the claim. All right, so now for a flow theta, we define its energy to be energy theta is summation over E belongs to E, the edge set, theta E squared times RE. And notice that here it doesn't matter whether we are taking which orientation of the edge we are taking, because after we are squaring it, so antisymmetric square of an antisymmetric function is the symmetric function. So we get this. Now Thomson's principle says that the effective resistance between A and the source and sink is the infimum of the energies where of all the flows theta, where theta is a unit flow from the source to the sink. And this is quite a break. It is quite a heavy result, which will allow us to do many things. But again, I gloss over the proof of it because of time mostly. Yeah. So now the next thing that we see, an important corollary of this is a Rayleigh's monotonicity principle, which says that if we have if you have a network and if you have two allocations of resistances on the vertices of the networks, such that in one of them, each of them is dominated by each resistance is less than the corresponding resistance on the edge on the other allocation, then the effective resistance in the former is less than or equals to the effective resistance between source and sink in the latter configuration. And the way to prove it is that we just notice that the energy of each unit flow um, for the first allocation is less than the energy for each unit flow for the second allocation according to the definition. And when we take infimum, so the infimum is of one of the left hand side is also less than the infimum of the right hand side, and then applying Thomson's principle proves the claim. Now we come to the most important part of this lecture, the main core of this thing, which is Nash-Williams inequality, the reason why I had discussed so many things. So, so given a subset pi of the edges, it is said to be a H cut set separating A from Z, the source from sink, if every path from A to Z includes an H from pi. So if you, in other words, if you remove all the edges from pi, then we cannot reach the from the sink from the source. And the Nash-Williams inequality says this, that if pi k are disjoint H cut sets separating A from Z, then the effective resistance between A and Z is at least as large as summation over all the k summation over E belongs to this pi k, conductance at E, and inverse of that. So this is the thing, and we shall prove it. So the way we prove it is, first we prove a more preliminary bound. So we say that if theta is a flow from the source to sink, and if pi is a cut set separating A from the source to sink, then sorry, this is the sum. I think I missed that the slash in analytics. So yeah, if summation over E belongs to pi, the absolute value of theta E is greater than or equals to strength of theta. And again, this can be done by a double counting argument. Suppose X and X, S is a set of all those X such that A and X are connected in G, set minus the cut set. Thanks to the node law, which holds for all X belong to S, X not equals to A, one has that summation over X belongs to S, summation over Y, theta XY is the strength of the flow theta. But also thanks to antisymmetry, one has summation when we take the sum. So this is essentially summation X belongs to S, Y does not belong to S, because otherwise if Y belongs to S, then theta XY plus theta YX both terms appear and they add up to 0. And this is less than or equals to summation E belongs to pi theta E. And this proves the claim. Okay, so yeah, this proves the claim. Okay, so now now returning back to the proof of Nash-Williams inequality, let theta be a unit flow from A to Z. Now, thanks to Cauchy-Schwarz inequality, for all k, we have that summation E belongs to pi k, Ce times this quantity, this Re energy of restricted to the ones edges in this pi cut set is greater than or equals to summation E belongs to pi k square root of Ce times square root of Re times absolute value of theta E and whole square. And that is equals to, because the Ce and Re are reciprocal, so that can get cancelled and we get this. And by claim 1, the right hand side is at most is at least the strength of the of theta, which is 1. Square of strength of theta, which is 1 square is 1. And thus our summation over E Re theta E square is greater than or equals to summation over when we take this to the right hand side, it becomes summation over k, summation E belongs to pi k, Ce inverse. And finally, by applying Thomson's principle, we get the proof. So now I'll come to the main problem. The problem, this was actually shared by Professor Andar Bandhavada in one of our semesters he taught us, and he asked that he told that it's a very challenging problem. I took the challenge and I spent one entire summer trying to solve this, and finally I could solve it. And so I'll present it to you now. Suppose a chess knight performs a symmetric random walk on a bi-infinite chessboard. So it has infinitely many rows and infinitely many columns. And we see that the knight move, we know that from the rules of a knight move that it is irreducible. Knight can visit its neighbors after, I think, 3 moves suffices to revisit its neighbors. So it makes sense to ask whether this walk is transient or recurring. So thanks to irreducibility, this is a meaningful question to ask actually, because otherwise states are transient or recurrent, but the entire walk is transient or recurrent only if the chain is irreducible. So we shall show that this above walk is recurrent. So the way we show it is, we view the chessboard as a network where the cells are the nodes, and between 2 nodes we have an edge if the knight can move from one of the cells to other cell in one move. And we put one unit conductors on each edge because we want our knight to move uniformly at each step. Now let the knight begin at the node 0, 0. So we label the nodes according to the row index and the column index. So let the knight begin at the node 0, 0. We have the following, consider the following cut set. So let B0 be the set with the point 0, 0, let B1 be the 5 by 5 section of the board centered at 0, 0. And in general, let Bn plus 1 be the part of the strip obtained when we add 2 rows above Bn, 2 rows below Bn, 2 columns on each side of Bn, and then take out Bn from there. So, for instance, B2 will be the strip obtained by by cutting out the 5 by 5 by cutting out B1 from the 7 by 7 section centered at 0, 0. Now, for each n, we define En to be the set of edges that have one endpoint in Bn minus 1 and the other endpoint in Bn. So it's like the knight moves from Bn to Bn from Bn minus 1 to Bn by passing through this cut set En. Then notice that these Ens are cut set separating 0 from 0, 0 from infinity, in the sense that if a knight has to somehow reach the band Bm starting at 0, 0, then it has to go through one of the edges in each of E1 to En minus 1. And also observe that by the construction of by virtue of construction, the EJ are disjoint because their endpoint sets are disjoint because of BIs are disjoint. And finally notice that the sum of conductances on all the edges in En is basically the number of edges in En, which is because of the unit conductance, we have equal conductance on all of them, which is at most the number of cells in Bn minus 1 times 8, because the knight has 8 possible ways, 8 neighbors, you can move 8 neighbors. And the number of cells in Bn minus 1 is bounded by C times n log n due to a construction, where C is an absolute constant. It doesn't absolute constant, and it does not depend on n. So thus the number of edges in En is at most 8 times Cn log n, and this summation over 1 by n log n diverges, and by an application of Nash-Williams inequality, we get that this random walk is recurrent. And this concludes my presentation, and thank you.
Okay, thank you, Aditya. Are there any questions? Of course, you can also ask Aditya afterwards if you want. Okay, so if not, then let's thank the speaker.